So we closed out chapter 4 last week, and we're looking at chapter 5 today, or at least starting chapter 5 today. Don't forget that you have your first two tests that have been posted, and we'll talk about this next one when we get closer to it. Right now, we're looking at 5.1 probability rules. So, probability is the measure of the likelihood of a random phenomenon or chance behavior occurring. The large numbers, law of large numbers. As the number of repetitions of probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. All right. So now the homework grades, there are no locks on anything. So homework grades or and no grade stops you from taking any assignment. So if that's what you're asking, hopefully that's I answered your question. If not, let me know. But yeah, there are no locks on anything, so nothing prevents you from taking anything, as many times as you want. Now the only lock is that you can take any test that I post, you only can take it twice, to get the best grade possible. So if you feel like you want to jump ahead, come back, everything's open for you to be able to do so. If you wanted to go take a look at chapter 10, you could, and then come back and all that type of stuff. Mess up the chapter 10, wait to get instruction, go back and work on it later and stuff like that. All right, so an experiment is any process with uncertain results that can be repeated. Not a problem. So an example of that is flipping a coin. All right, sample space, the collection of all possible outcomes of an experiment. So when you talk about flipping a coin, the sample space of flipping a coin will be heads and tails. It's all possible outcomes. And that's denoted by S. All right, so S will represent our sample space. Your event is any collection of outcomes from the sample space. So if you want to know the probability of landing tails, tails would be your event. And so that's denoted by any capital letter. And of course, you wouldn't want to use S because S represents your sample space. All right, rules of probabilities. P parentheses E. Where's my pen at? There we go. And normally you call that P of E. That represents a probability of event E. So your probability would be between 0 and 1. So that means it would be between 0 and 1 inclusive. That means it could be equal to 0, could be equal to 1 as well. The sum of the probabilities of all of your outcomes is equal to 1. So if you were to look at the probability of each individual outcome, they will add up to 1. So those are the first two rules that they give. All right. So the probability model must satisfy rules 1 and 2. So we have here, verify that this is a probability model. So they give us a chart that has colors: brown, yellow, red, blue, orange, green. And the probability of getting brown is 0.13, probability of getting yellow 0.14, getting red 0.13, blue 0.24, orange 0.20, and then green 0.16. So in order for this to be a probability model, it has to satisfy both rules 1 and 2. So rule 1, each probability is in between 0 and 1. So that is the case. And then rule 2, each one of those probabilities, the sum of each one of those probabilities need to be 1. And so we look at adding up 0.13, 14, 13, 24, 20, and 16, you end up getting 1. And since the probability satisfy rules, yep. Since the model satisfy rules, and I probably should have said model here. Since the model satisfy rules 1 and 2, it is a probability model. All right. An event is impossible if the probability is zero. We talked about it that it is possible that your probability could be equal to zero. An event is a certainty if the probability is equal to one. The closer a probability is to one, the more likely the event will occur. The closer a probability is to zero, the less likely the event will occur. An unusual event is an event that has a low probability of occurring. All right, so typically an event with a probability less than 0.05, or in other words, 5%, is considered unusual. That's what we will use as our standard, but it's not set in stone. So if you were doing this on your own, or someone else were to give you another standard, then that's fine. That's what we will use once again, but that's not necessarily set in stone as far as considering that it is unusual if it's less than 5%. All right, calculating probabilities. Let me write this better. We have the empirical approach. The probability of E is the frequency of E over the number of trials of the experiment. All right, so an insurance agent currently insures 182 teen drivers. Last year, 24 of them had to file a claim. Based on these results, what is the probability that a teenager will file a claim in a given year? So I'll give you a chance to write it down. All right, so 24, last year you found out that 24 of them had to file a claim, 24 out of the 182 teenage drivers. So you would just put the 24 over the 182, and that would be 0.132. All right, so after you get that 0.132, my math lab will give you statements that you would choose from in order to figure out, in order to make a correct statement. You just pick the one that makes the correct statement. So you will see something like what's in purple. It says for every 100 teenage drivers, we expect about 13 to have to file a claim. So where they would get that and what you would get that answer from is you would take the 100, multiply it times whatever your probability was. In this case, it was 0.132. 100 times 0.132 is 13.2. So that's about 13. So what you would do is, like I said, take that number that they give for every 100. So they said for every 1,000, you would take 1,000 multiplied times the 0.132. So it would have said for every 1,000 teenage drivers, we expect 132 to have to file a claim because you would have multiplied the 0.132 by 1,000. So whatever that number is that they put in the statement, you'll multiply it times your probability, and then make sure you have that number in the final piece of that statement. And that would be the one that you would choose. That would be the correct one for you to choose. Any questions? All right, so that was the empirical method. Here we have the classical method. Take the number of outcomes in E, place it over the number of outcomes in your sample space. And so we have N of E over N of S. So that's how you would say that. But that's just notation for the number of outcomes in event E over the number of outcomes in the sample space. So a quick example, we've already talked about flipping a coin. Initially when we were explaining the experiment, sample space, and event. So if we're talking about flipping a coin and landing tails, it's always easiest to establish your sample space first. In other words, you look at all possible outcomes. So our sample space is heads and tails. And the number of outcomes in our sample space is 2. Number in our event, well, our event is tails, because when I coin to land on tails, the number of outcomes in our event is 1. So you take the number of outcomes in your event, place it over the number of outcomes in your sample space, and we have 1/2. And we already knew we have a 50% chance of landing heads versus tails. And this is just the way you would calculate that. All right, questions? All right, any problems before we scroll up? All right, here we have a single dice roll. What is the probability of landing a number greater than 2? All right, so when we look at a single die, we have the options of 1 through 6. All right, so that means our sample space over here is 1 through 6. And so the number of outcomes in our sample space is 6. Now, I want to emphasize this right here, that this 6 and this 6 are not the same 6. In other words, if I had 1, 2, 3, 4, 5, 8 right here, the number of outcomes would still be 6. Okay, so I don't want you to confuse those numbers and saying that since it ends in 6, that's why that 6 is there. No, that's the number of outcomes. It could be 1, 2, 3, 4, 5 triangle. The number of outcomes will still be 6 because we have 6 outcomes in our sample space. Okay, so just wanted to point that out. Now our event is the number of outcomes that are greater than 2. So that would be 3, 4, 5, 6. So 4 elements fit that description. All right. So now we place the number of outcomes in our event over the number of outcomes in our sample space. So that's 4/6. Don't forget to reduce the fraction. There's 2 that's in common with both top and bottom, and that's 2/3. And that's our probability. Any questions? All right, next one. A pair of dice is rolled. So this time we have a pair of dice, not just a single die. A pair of dice is rolled. Compute the probability of rolling a 7, and then compute the probability of rolling snake eyes. All right. So once again, first thing we want to do is establish the sample space, the number of our sample space. I'm going to go ahead and write establish. So when we talk about the different combinations that can be produced by two different die or two different dice, yeah. You're talking about, landing one and landing one for both, and landing one for die one, and then landing two for die two, landing one for die one, landing two, three for die two, and you're talking about all of those different combinations. So the easiest way of doing that, instead of trying to list them all out and possibly missing a combination, is that if you know that you have 6 options for die one and 6 options for die two, you can just multiply those two numbers together. It's called a fundamental counting principle, and that will give us 36 total options or 36 total outcomes. All right. So if I knew I had 6 faces on die one, but 8 faces on die two, it would be 6 times 8, which would be 48. So number of possible outcomes. All right. So first event, we want to know what's the probability of rolling a 7, so we can examine those possible outcomes. Talking about right here. So you're talking about die one being 1 and die two being 6. Then 1 is 2 and die two is 5. Then we got 3, 4. And then 4, 3, 5, 2, and 6, 1. So we have 6 possible outcomes of rolling a 7. All right. So once you've established the number of your sample space and then the number of your event, you have 36 and 6. Place the 6 over that 36, and 1 out of 6 chance of rolling a 7. All right. So B is rolling snake eyes. Hold on, let me see something. Okay, I didn't do that. So B is rolling snake eyes. So in other words, rolling a 2. We already established what our sample space is, so the number of our sample space is 36. And then here, the number of our event is 1. There's only one way to roll a 2. That's if die 1 is 1 and die 2 is 1. So it's just a 1 out of 36 chance of rolling a 2. Any questions? Any questions? I think this is the last one out of, yep. Okay. So next one, suppose a survey asked 500 families with 3 children to disclose the gender of their, erase some of this stuff, we get to it. The gender of their children, and found that 180 of the families had 2 boys and 1 girl. You chance to write that before we get into the questions. So A is estimate the probability of having 2 boys and 1 girl using the empirical method. And then B, compute the probability of 2 boys, 1 girl using the classical method. All right. Thanks for your chance to finish writing. All right, so A is to estimate the probability of having 2 boys and 1 girl using the empirical method. So using the empirical method, we have 500 families total, and we found out that 180 of them had 2 boys and 1 girl. So all we do is take that 180, place it over 500, and that'll give us 0.36. My math lab will let you know whether they want to answer in decimal or fraction. I think in this one, or in the book, they could just convert it to a decimal. And so that's why I did so. Questions on A? All right, B, the classical method. So we would have to explore all possible outcomes of getting 2 boys and 1 girl. So you first start off with having a boy. After you have a boy, there are only two possible outcomes. You have a boy or girl. And then from that second boy, you can have a boy or girl. Or from that second girl, you have another boy or another girl. Then we would do the same thing with the idea of having a girl first. And then a boy or then a girl. Then after after the second birth, if the second birth is a boy, then you will explore having a boy and a girl, boy or girl. But if that second birth is a girl, you explore having a boy or girl. So you see that we have 8 possible outcomes altogether. You know, boy, 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 girl, boy, and all the way down the line. But then if you're talking about how many different outcomes would be for 2 boys, 1 girl, and you know, that's our event. So we have 2 boys, 1 girl here, 2 boys, 1 girl here, and then 2 boys and 1 girl here. So we have 3 different scenarios in which we have 2 boys and 1 girl. All right. Questions before we finish off this problem? All right. So the probability of getting 2 boys, 1 girl using the classical method is 3/8. Questions on anything? Questions? All right, so that's it for 5-1. Checking something for 5-2. Gotta do both of those together. Yep. All right. So looking at my math lab, we only had a couple people that were in chapter 4. So once again, I'm gonna give you a chance. Of course, we can't come to class and not do anything or cancel classes or whatever. So we only did one section today. Next class, we'll probably look to do 5-2 and 5-3. But please don't sleep on this work. Make sure you're getting it done. Get in there and knock the stuff out. So any questions before we dismiss today? Any questions, concerns, comments? All right. So you guys have a good one. Be safe. And I will see you on Wednesday.
I don't think. Oh, go ahead.
I just said thank you.
Thank you. No problem.
Okay, so yeah, I think you answered my question, but I know how Zoom used to work. Can you hear me?
Yeah, hold on. Let me cut off the recording.